So what about regulation of this pathway? Flux is largely controlled at the first step in the pathway, performed by carbamyl phosphate synthetase 2. It again is regulated allosterically by UDP or UTP. Similarly to purines, right? This pathway's final product, or real first final product, is UMP, which can then be converted to UDP and UTP. Well, those downstream products come back in feedback inhibition. But again, this step is tightly regulated because it can also be activated. Just like how PRPP activated purine biosynthesis, it also activates this pathway. So that is not new. However, what is new is that ATP also activates this pathway. Why does that make sense? So ATP, right, is a purine. And a purine is activating the synthesis of pyrimidines, So in our bodies, right, the hydrogen bonding is happening between a purine and a pyrimidine. So we also want about the same levels of purines versus pyrimidines. So it makes sense that if we have a lot of ATP, a lot of purine, we should activate pyrimidine synthesis to equalize the levels of the two types of nucleotides that eventually, in DNA, need to base pair. There is a second level of regulation here at OMP decarboxylase, a little bit of feedback inhibition there from UMP. So largely regulation of the synthesis of purines and pyrimidines is meant to balance the levels of purines versus pyrimidines. But also when we were looking at purines, we could see kind of balancing within purines as well. The story isn't quite over yet though, folks. How are deoxyribose nucleotides made from ribonucleotides? So DNDPs are made from NDPs. So deoxyribonucleotide diphosphates are made from ribonucleotide diphosphates. And this is a single reduction reaction by an enzyme ribonucleotide reductase. Now, the exact mechanism of this enzyme is not known, but it is thought to be via some type of free radical mechanism, possibly using a radical tyrosyl group, just like we saw with complex 4 in the electron transport chain. So it's actually the R group of a tyrosine that performs the radical chemistry, which is kind of interesting. And that gets us from this hydroxyl group to a reduced hydrogen. Of course, this process is also regulated, but there's only so much that we can learn in one set of videos, right? And once we have converted the NDP to the DNDP, the deoxyribonucleic acid, we can finally get to DTMP. So what's happening after we convert the ribonucleic acid to the deoxyribonucleic acid, right? We have the DNDP. What happens is just a really quick hydrolysis to get to the monophosphate, the DUMP. And once we have that DUMP, we can do a chemical reaction to get to the DTMP, and bam, there goes synthesis of DNA. We have all 4 of our nucleotides required. This is performed by thymidylate synthase. This enzyme is performing the transfer of a methyl group That is the only difference, right, between uracil and thymine, this methyl group here. The transfer is performed with a cofactor that we've seen before, THF. This is folate. But the one carbon transfer is a little bit different. We saw transfer of formal groups in purine biosynthesis. This is transfer of a methyl group, so we're using a slightly different version of the folate cofactor. During this process, unusually, the folate also becomes oxidized. So for this reaction to occur over and over again, right, we would need to regenerate the dihydrofolate, DHF, back to the tetrahydrofolate, the THF. One interesting point about this process here, folks, is that DTMP synthesis is a main target of many cancer therapies. So, right, cells can't grow without having thymine to incorporate into their DNA. So this is a good place to target for cells that require a lot of replication of their DNA. And if you can believe it, that wraps up our final series of videos, our first real series of videos about an anabolic process. We learned about nucleotide synthesis. It's pretty complicated, so don't focus in on the various enzymes that we talked about, but do focus in on the regulation. Also recognize that when we saw purine and pyrimidine synthesis, we had some common substrates being used frequently and common cofactors. We saw glutamine, aspartate, ATP, THF quite a bit. When we focus in on the regulation of these pathways, we should understand that allosteric regulation is the main way to control flux. We saw both inhibition and activation. We should understand why this regulation makes sense. Finally, we saw how DNDPs were made from NDPs, just a quick reduction. With that, I'll leave you with the last meme of class. It doesn't have a picture of a cat, but it's still about cats. See ya.